We're now going to turn our attention to a discussion of acids and bases, and there's a few different definitions you might remember from general chemistry: the Bronsted-Lowry definition, the Arrhenius definition, and the Lewis definition. We're going to spend most of this chapter discussing the Bronsted-Lowry definition. And a Bronsted-Lowry acid is a proton donor, and a proton, when you hear that term, just think of H+. So this is really anything that has a hydrogen on it, can potentially act as an acid. A Bronsted-Lowry base is a proton acceptor. And the thing that we're going to consider a proton acceptor is going to be a lone pair. And we'll find that we'll have a lone pair on an atom. It can be a neutral atom or negative. So let's consider a general acid-base reaction. Here we have HA, so this is something with a proton. That's going to be our acid. We have B with a lone pair. That's going to be our base. In this case, it's negatively charged, but it doesn't have to be. And what happens in an acid-base reaction is the base accepts the proton from the acid, or the proton goes to the base. So what we end up with is the proton bonded to B, and then A is left over with a lone pair, and that will be A minus. In the product side, we have our conjugate acid and our conjugate base. Just think of this right side as a new acid-base reaction. So to figure out which is which of these would you pick as the acid? You would pick the species that has the proton. So that's the acid. Because it's on the right side, we call it the conjugate. And then the species with the lone pair is our base, but because it's on the right side of the equation, we call it the conjugate base. We started our discussion of curved arrows when we were discussing resonance. So remember, we can use curved arrows, and what curved arrows do, they show electron flow. When you're drawing a curved arrow, you always start at electrons, and then the head of the arrow points to where the electrons are going. So let's apply this to our acid-base reaction above. I have this lone pair on B, the base. That's where we're going to set our pencil down and start, because we start at the electrons. These electrons are going over here to the proton to form a bond. That's where they're going. And then, if I highlight this bond between H and A, well, we can't have two bonds to this proton because we're forming one bond, and hydrogen can only have one bond. So as we form a bond, another bond has to break. And this bond that I've highlighted in purple, that will break away from the hydrogen, and those electrons will go on to A as the lone pair. So it was the lone pair on B that formed the new bond with H. So in the product, those electrons are now those electrons between H and B. Then this bond between H and A went on to A as a lone pair. So that's where those electrons ended up. Again, the head of the arrow shows where the electrons are going. These electrons are going to the hydrogen. These electrons are going to A to form the lone pair. Now, one place that I don't want you to get confused is where we've transitioned from resonance structures to a chemical reaction. In both cases, we show electron flow with curved arrows, but resonance structures and chemical reactions are two totally different things. So in resonance structures, we had certain rules, like we could only move lone pairs and pi bonds, we can't move sigma bonds. In chemical reactions, we are moving atoms, so we join B with H, and we're also moving sigma bonds. We're moving the sigma bond here over onto A as a lone pair. You can do that in a chemical reaction. You can't in resonance structures.